Welcome back, nerds. I hope everybody's feeling fantastic today. Get out of the way. We started this lesson, section 1.2, and on Friday, and it's going to take us a minimum of at least one more day after today, probably 2 more days after today. Anyway, the last thing that we talked about was increasing, decreasing, and treating increasing, decreasing like riding a roller coaster. Instead, as we go from left to right, if your roller coaster had to go up, your graph was increasing. And as you go from left to right, if your roller coaster would go down, you're decreasing. If it's flat, perfectly flat, constant. And, something I really don't like, but we have to do it this way because it's what College Board wants. At the boundary between increasing, decreasing constants, when we change from one to another, we are going to use brackets. So College Board has decided that at this point, this graph is both decreasing and constant at the same time. And at this boundary point, this graph is constant and increasing at the same time. I would argue that it is neither, but I don't get paid those big bucks, so it be what it is. Okay. For these two questions, what we've been tasked with doing is using a graphing calculator to figure out on which intervals we're increasing, decreasing, and possibly constant. Now, I would hope that you could graph this without a graphing calculator. I'm going to still, but my point is, I would hope that you know that it's a quadratic, a parabola. I'd hope that you know it faces up because there's not a negative sign in front of it. And I would hope that you would know that its vertex is at -2, 0. Because this is just the parent function x squared that's been shifted to the left 2, and that's it. So -2, 0. I'm going to sketch that parabola that I just described. And if you throw in a 0, you'll get 2 squared, which is 4. So there. So this is somewhat what the graph looks like. And just in case you don't believe me, go to handy dandy graphing calculator. And we'll go to y equals, parentheses, x minus 2, parentheses squared. That's what I said. I'm glad you caught that. And just in case you had a goofy window the last time you graphed, hit zoom 6 instead of the graph button. Zoom 6 will always get you the 10 by 10 by 10 by 10 XY axis. There we go. So that's pretty much what I had. Okay. Great. If you were riding this roller coaster from left to right, as a class, so I'm looking for 26 minus whoever's absent voices, I just want to know at the edge of the domain to the far left, class increasing or decreasing? Only about half of you spoke. I bet it won't even show up on the YouTube video. About half of them whispered decreasing, and the other half were scaredy cats. But why is the question? The answer is yes, it's decreasing. And I would say that the reason why the other half of you didn't speak was because you weren't sure because this graph points up forever. And what's happening is to those people, you're thinking about the y values. We don't care about the y values. All we want to know is what are the slopes of this graph? What do you mean slopes, Mr. M? I thought you said, roller coaster car. Okay, yeah. But in all actuality, when we talk about increasing, decreasing, we're talking about what the slope of the curve is at a specific place in space. So take this x value, for example, right here. I'm not even going to give it a number. It tracks to that point right there. If I were to draw, let me use my nerd paper here, a straight line. Actually, you can't see that. If I were to draw a straight line that touches that point without going through the graph, By the way, that's called a tangent line. This line would have a negative slope. So everywhere on the left side of this graph, these lines would have negative slopes. At what x value would they stop having a negative slope? -2. At the vertex, we stop having negative slopes. And actually at the vertex, technically you have a slope of 0 because it's horizontal. My paper's crooked. So we are decreasing on the left side of this graph. We decrease from negative infinity all the way until what happens to be the vertex of this graph at -2, and College Board wants us to bracket the boundaries between increasing, decreasing change. And then after -2, this would be the time where all of the lines that I could draw would have positive slopes. Therefore, it is increasing after -2. For the rest of its domain. Again, not caring about the y values, asking how the graph is behaving. As we go to the left, from the left to the right, are we falling or rising? Okay. Questions on that? Are you ready to go for another example? Let's go. Okay. I'm going to hyper-exaggerate this graph just because it makes it easier to see what's going on, and then I will put it on a graphing calculator. Later in the year, we'll graph these without a graphing calculator. This graph has a horizontal asymptote and 2 infinite discontinuities, 2 vertical asymptotes. I'll sketch those on here with red. Of course, the graphing calculator is not going to put asymptotes on there, but we will. And what we get is this. Like that. Man, that is not pretty over there. The staple schooled me. Sorry. Let's get on the graphing calculator. Go to y equals. I'm going to clear that graph. Now, because I am using an 84 plus, I can do stacked fractions. If you're not using an 84 plus, when you type your denominator, you need to wrap the entire denominator in parentheses. I'll show you what that looks like. If you don't wrap the denominator in parentheses, it thinks the -1 is after the fraction. It thinks the fraction's x squared over x squared, which it'll simplify to 1. And it'll subtract 1, and it'll graph y equals 0. So you have to use parentheses for your whole denominator. If you have an 84 plus, alpha, y equals, and the very first option is your stacked fraction. And there it is. Now I'm just going to type it what we see, x squared, go down, x squared minus 1, alpha y equals, is hers not working? Does alpha y equals work on that? I'll pause the video while she ignores me. Okay, that was a fun little aside. There we go. All right, so again, zoom 6 typically, but I did just see that my graph is a 10 by 10 by 10 by 10, so I'm just going to hit graph. Boink! And it's going to give me something similar to what I drew. Now mine's hyper exaggerated so I can see the asymptotes better, but there it is. Now just so we're clear, remember this graphing calculator, like Minecraft, it doesn't do round things, it only does straight things. So it has to shade using pixels. So I'm aware that it looks like it straightened out over here, and I'm aware that it looks like it straightened out over here, but it didn't. And if we were graphing this on Desmos, you'd be able to zoom in far enough to see that you do still have a slope. it will not be flat. So even though mine looks a little drunk, it's what's actually happening. Okay? Okay. Shut this off. So we look to the far left, way over here. We put our roller coaster car way over here. We start writing. As we head to the right, the car is going to have to go which way, up or down? Up. So are we going to be increasing or decreasing? Increasing. We will be increasing at the beginning of this domain. So we begin increasing from negative infinity, and we will stop increasing. Technically, we have to stop at -1. Now, we'll never reach it, though. You see, -1 is an infinite discontinuity. The graph doesn't exist there. So what we'll do is we'll say, with a parenthesis, not going to put a bracket there because my graph doesn't exist there. I can't bracket a value my graph doesn't exist at. But let's get past -1. Now we're here. And if my roller coaster car is sitting on this track here and it's still moving to the right, is it going to be going up or down, class? It's going to be going up, which once again means I'm still increasing. I simply can't include the -1. So we want x value. I'd be looking for lots of voices to just say the number. At what x value does my graph stop increasing? 0 it is. And that one is a boundary. So it gets a bracket. Because at x equals 0, starting right here, my roller coaster starts falling, which is decreasing. And just like before, with this infinite discontinuity, I cannot include this infinite discontinuity. So I will be decreasing forever, trying to get close to x equals 1. But I'll never get it. After x equals 1, my roller coaster's here, and then once again, falling for the rest of the domain. Now I need to make sure that the idea of increasing, decreasing, using domain values only, when to use parentheses, when to use brackets, I need to make sure that that idea is perfectly clear. Are there any questions or fogginess I could try to help clear up or double explain? Yes, ma'am, Diane.
How did you get the decreasing domain?
So decreasing is going to be anywhere my roller coaster would have to fall. So it'll be going this way. So I decrease from this x to this x. Now I can't reach this x because it's not allowed. But then once again, over here, remember we're always moving to the right. So again, falling there as well. And since the graph never stops, we will continue to fall for all of eternity. Now, I'm falling towards this y value, but I would never actually get there. So we would technically still try to get to it forever and ever and ever and ever and ever. Okay? Okay. Any other questions on it? That's a good question. No? Okay. Well, let's talk about extreme values then. Extrema. Local and absolute extrema. There's a lot of words here. I would rather go look at other pictures. I'm going to turn back a page and just point here and describe what's going on. These 2 points right here are called local minimums. Local means in this general vicinity. This point right there is a local maximum in this general vicinity. So hopefully just by looking at a picture, it's a little bit obvious what those terms mean, minimum and maximum. when we say what the minimum or maximum is, we're using the y value. Oh, the minimum is 5. And then you would say, where? Oh, at x equals 2, something like that. So where a minimum or maximum occurs is an x. What its actual value is a y. Other than local, we also have the terminology of global and or absolute minimums and maximums. And it means the same thing. Global max, absolute max. They mean the same thing. What does it mean to be the global or absolute max or global absolute minimum? It means the highest or the lowest point on the entire graph. That's what that means. That was me, I think, tapping on the table. Sorry. So even though both of these are local minimums, this one is also the global or absolute minimum. Does that make sense? This one is a local maximum, but because this graph, I guess the thought is it goes up forever, it has no global maximum. So at least comfortable with what those terminologies mean? So what is important in that box is what is in bold. A local maximum occurs when a function changes from increasing to decreasing at a point on the domain. I included the at a point on the domain thing because let's just say, for the sake of argument, my graph had started decreasing at -1. Since -1 is not on my domain, I wouldn't have said that was a local anything. It has to be a point that exists for the graph. So if you go from up to down, like we did right there, you have a local maximum. So x equals 0 has a local there is a local maximum at x equals 0. That max value there happens to also be 0, coincidentally. When a graph goes from decreasing to increasing, then you have a minimum, like right here. We have a minimum of 0 at x equals -2, because my graph went from decreasing to increasing. Cool with that? Yeah? Okay. Basically, you're looking at bumps. Tops of bumps are maximums, bottoms of bumps are minimums. Easy peasy. So here we have a function, a polynomial, that we could graph by hand later in the year when we review concepts like synthetic division and the rational root theorem and all that stuff. Until then, we will use a graphing calculator to graph it. And until you learn some calculus, you will never find minimums and maximums by hand, unless they happen to be a very specific type of point. So let's graph this on our graphing calculator. Got it turned on, go to y equals, clear it out. Here's our x button, boink. Raised to the is the caret symbol right here underneath clear, and fourth power. My calculator is still sitting in the exponent position, so I have to hit the right arrow to get out of exponent position. Minus 7x squared, squared button on the left-hand side, plus 6x. Last time I graphed, I was in the standard zoom. So I'll just hit graph. Oh boy, I can see a lot of the graph, but not all of the graph. Sure would be nice if I could see, quote unquote, all of the graph, right? Because we could see there's a minimum down there. Let me show you some features of our calculator. First, I'm going to show you one, and I'm hoping you will instantly see why I don't like to use it. So you can see that this thing has a wiggle in the middle of it, right? Zoom, and if you scroll down far enough, eventually you find zoom fit. And students think, oh, this is going to be great. It's going to show me everything that's important about this graph. Oh boy. So the wiggle in the middle of the graph is gone, isn't it? No, it's not actually gone. You know what happened? The calculator zoomed out so stinking far you can't see it anymore. In fact, this y-axis goes above 9,000. Oh, I screwed up. Okay, we're going to pretend I didn't say anything. Instead, what I'm going to say is this y-axis, it's over 9,000. So I can say it like that. Okay, there. And those of you that know, they know. Okay, those of you that don't, sucks. Anyway, the point is our graph zoomed out really far. That's why I don't ever use zoom fit. What it attempted to do was show you the entire graph, but the graph goes on for all infinity. And you can't do that. So go back to zoom 6. Now you know why I don't use zoom fit. And instead what I'm doing is I'm just going to adjust my window, and you need to dip down far enough. How far down on that y-axis is literally just an educated guess. So somebody give me a negative number.
Negative 1.
Negative 20. Let's try it. Let's go down to negative 20. I don't want to have 30 tick marks. Space between negative 20 and 10 is 30, so I'll just say go by 3s, and I'll have 10 tick marks. Not quite. We still missed the bottom of it. So 30 wasn't enough. I would just go to 50 at that point, negative 50. Oh, wait, you said 20?
Yeah.
Maybe negative 30 is enough. Let's see if negative 30 works. Okay, that worked. Great. Our job was to find all the extrema and where they occur. So what are the y values and where did those things occur? I'm going to go ahead and sketch this. It looks like it crosses the x-axis at 0, 1, 2, and negative 3. That's what that looks like to me. 0, 1, 2, negative 3. Picture not drawn to scale. There. Notice I didn't put any y values on mine. So we're getting away with drawing it however we want. Picture not drawn to scale. Isabella, you look incredulous. What's going on?
I grafted it.
Yes.
It does not look like your graph, so I think that's wrong.
Well, let's see. Bring it up.
No, I know I grafted it wrong.
Let's see. Bring it up.
You don't have to.
I'm going to pause the video for you. Okay. Problem solved. Now, anyway, we were about to find extreme values, right? Minimums are going to occur here and here. At what x values? I don't know. Mr. M, won't they just be halfway between 0 and negative 3, halfway between 1 and 2? I wish. No. It doesn't work that way. So we have to use the technology to find them, and there will be a maximum value here-ish. I don't know where. I just know it's between 0 and 1. The calculator can find those points, though. Do second, trace. So we're trying to calculate some stuff. And this is where our minimums and maximums can be found. I'm going to go after the minimums first because there's 2 of them. So second, trace, and then I'm going to type the number 3. Remember when we were doing second trace intersect? It was asking us, is this the curve? Is this the curve? Is this the guess? You have to, for this one, get left of the point you want it to find. So I'm just going to hold down left. So I know I'm trying to track down like that value. And by the way, you can't just go like, oh, that's it right there. No, you have to actually calculate it. So go to the left of the bump. Now it wants you to go to the right of the bump and go between those two. There you go. So go left, enter, go right, enter, go between, enter. So right here, we have a minimum. A minimum of y equals negative 24.057. at x equals negative 2.057. Remember, for AP, we're always going to round to 3 decimals. That was this one. Now you just wash, rinse, repeat for this one, the other minimum. Second, trace, you can't see the screen, minimum. So it says get to the left of where the answer is. That's to the left of the bottom of the bump. That's to the right of the bottom of the bump. Go in between and hit enter. And we'll see we have another minimum. Of y equals negative 1.766. And that's happening at x equals, to 3 decimals, 1.601. And then lastly, that maximum value that's happening right there in red, second trace maximum. And the nice thing about that is, whoops, I pressed the wrong button. The nice thing about that is it's the same instructions, left, right, guess. So to the left of the bump, to the right of the bump, in between those lines, and we found our maximum. Is that 324? Yeah. At x equals 0.456. What do you think about using the calculator for minimums and maximums? No? You don't like it?
I like it. It's easy.
But it's a lot of commands that we have to know how to use. So intersect, minimum, and maximum are a big deal. Turn my calculator off now. Try to save that battery power. All the things are worked out. Let's talk about the last thing that we're going to talk about today, and that is concavity. Basically, concavity is just which way does my curve bend. That's what it is. And you only have 2 options. You're either bending up or you're bending down. However, there's 2 ways of bending up and there's 2 ways of bending down. So what I've drawn is what those kinds of curves look like. So if a curve is going up and to the right, I don't remember where I was before I paused the video. Something about, 2 different ways of curving up, 2 different ways of curving down. So these 2 are versions of curving up. These 2 are versions of curving down. So why are there 2 different ones? Well, concave up could happen on an increasing curve or a decreasing curve, as well as concave down could happen on an increasing curve or a decreasing curve. I mean, what is concavity? Technically, it's how fast the slope is changing. It's like the slope of the slopes, but you don't have to know that yet. I just kind of cheated and gave you some future knowledge. For right now, you just need to know it describes the way the curve is bending. And if a graph changes concavity, means it changes from up to down or from down to up at a point on the domain, then those kinds of points are called inflection points. So let's go back to this. Somewhere, actually, I'll just do like this. Trying to find something. There we go. Ooh, because it's black, the whole screen turns black. That's no good. That's no bueno. There, I'll just cover it with my nerds paper. There. The part of the graph that I have left uncovered, I'm hoping we can all agree is kind of bowl-shaped. That's concave up. The part of the graph that is still uncovered is bell-shaped. That's concave down. And once again, the part of the graph that is uncovered is concave up. What that tells me is this graph changes concavity more than once. Where, you might be asking? The answer is you don't know without calculus. Okay? But it is cool to know that somewhere around there-ish and somewhere around there-ish, coincidentally close to the x-axis, it is just a coincidence, this graph is going through a change from concave up to down and down to up. This graph has 2 inflection points. Now, for the one example that we're going to do, it is obvious where it is. And the reason why it's obvious is because this graph is symmetric. Sorry, I left the boxes on. And also, sorry, I typed those numbers wrong. I know. There it is. So it wants us to analyze the shape. Now, because I've had to stop and help people with their graphing calculators, and I've had to stop my penis drawers in the back. Oh, that's right, I forgot to pause it this time. So sorry, Noah and Mark. Huh? You weren't?
No, we grabbed his calculator and changed
You always the worst in them, huh?
The what?
You always look for the worst in them, huh?
The worst in them?
Yeah.
I'd say change the language to be worse than drawing penises.
No.
Yeah, that's what I was just thinking.
More appropriate.
That's a good idea.
I don't know.
I didn't do it.
Anyway, for purposes of time, I have time to cut up, but I don't have time to teach. Anyway, for purposes of time, we're going to go through the analysis a little bit quickly. I will tell you that I specifically chose a function that was symmetric around the origin, so that way I could guarantee that right there was the inflection point. So I can only guarantee that without calculus because I know for a fact that this graph is an odd function, it's symmetric around the origin, that forces that to be an inflection point. So what do I see? I see a graph that is increasing from negative infinity to this x value of negative root 3 over 3. Bracket. Then decreasing between the root 3 over 3's. Brackets. And then, of course, increasing after the positive root 3 over 3. All the way up to positive infinity. Now, I've already kind of given it away, but this is our inflection point, which means we have a change in concavity there. Everywhere to the left of that dot, bell-shaped, concave down. And everywhere to the right, bow-shaped, concave up. So we'll see concave down is negative infinity. Oh, hold on. College Board puts brackets on the barriers for increasing, decreasing, not concavity. Why? Good question. But there it is. So we just have to remember not to bracket our concavity changes. That was fun.